When we design our structures, it is not sufficient just to say that the 100 years flood is acceptable or 50 years of flood is acceptable for a particular infrastructure. We need to calculate the risk of the flooding. For example, if we are talking about the flood, risk of the flooding, not only the risk of the flooding, but also what are the consequences, what are the effects of those floods, right? So in some areas, uh, the same magnitude of flood may have less impact compared to the other areas, right? So we need to think from the larger perspective, what is the risk and what are the consequences of risk, how can we mitigate the risk, and its environmental, financial, economical, all different risks needs to be considered. Okay, now this is just an example to calculate the risk of flooding. So our structure is designed with 100-year flood. So the length of the structure could be different, right? So the number of years that the design that you design may be different, and generally is different than the flood magnitude. Okay, 100 years return period flood is different than the lifespan of the structure. So the structure is designed with 100-year flood. What is the risk that structure will be flooded in 10 years, 100 years, or 500 years, right? So what your lifespan of the structure may be 10 years, maybe 100 years, or maybe 500 years, but the value you take for the design is 100-year flood. Okay, you take the 100-year flood. So T is the return period, which is 100, and the probability of accidents in any given year is 1 over 100, which is 1%. So we set this as 1% AP, 1% annual accidents probability. Okay. Now we calculate the risk based on the accident. So 1 minus 1 over T to the power N. Okay, N is the number of years. So 10 years, 9.6%. The structure is going to be flooded at least once in next 10 years is 10%. The structure is going to be flooded at least once in next 100 years is 63%, right? So now this is the point. Your 100-year flood doesn't mean that it will come every 100 years. You can see from the risk, the 100-year flood has the risk of 63.4%. Okay, so the risk of that structure being flooded within the next 100 years, even though you design with the 100-year flood, is 63.4%, and 500 years is 99.3%, right? So there will be no 100%. Whatever the value you take, you can never reach the 100%. You practically, technically, it is very close, but you will not reach the 100% because there is no upper bound of the magnitude of the flood. So this is how you calculate the risk of flooding. Okay, so 1 minus 1 minus 1 over T to the power N, and T is the return period. Now let's see some other examples. A small dam is built with a return period of 20 years. So 20 years of return period. Find the probability the dam will be overtopped in any given year. So probability of accidents in any given year is 1 over T. So 1 over 20, which is 0.005. The probability that the dam will not be overtopped in any given year is just the opposite of that, right? So 1 minus 1 over T, 1 minus 0.05 is, I think this is a mistake, should be 0.95, right? So this should be 0.95. Now the probability that dam will not be overtopped in next 3 years. Okay. Now probability of dam will not overtopped in next 3 years means will not be overtopped next year is 1 over 2. Again, it will not be overtop is 1 minus 1 over 2, and again in the third year 1 minus 1 by t. So you multiply those three probabilities and the value you get is 1 minus 0.05 to the power 3, which is 0.857. So the probability that the dam will not be overtopped in any given year is 0.95, but the dam will not be overtopped in next 3 years is 0.857. Okay. Now next one is probably the wall overtops exactly once in 3 years. So we have these two things here. One is the probability of overtopping and the probability of not overtopping, right? So these are the two options. So either will overtop or it will not overtop, right? So here in this example we have not overtopping in 3 consecutive years. So that is how we calculate the probability. Now probably the wall will be overtopped at exactly once. That means uh, first year, let's assume first year it will be overtopped, and then second and third year it will not be overtopped. So that is one option that could be possible. Plus the probability that first year it will not overtop and then second year it will be overtopped and then not overtopped as well. So the second and third one is first year it is not overtop, second year also not, and the third year it overtop, right? So you add these three and then you get the total probability. So this is 3 times 1 by 20, 1 minus 1 by 20 times 1 minus 1 by 20. You just substitute the values because both has 1 1 over t and 2 1 minus 1 over t. So 3 times this, and that is 0.135. Now the last one is the probability, SPE, probability the wall overtops at least once in 3 years, right? So that is opposite of it will not overtop in 3 years, right? So that means 1 minus whatever it is, 1 minus 1 by t to the power 3, which is 0.143, right? So this is how we calculate, but these values are not that much useful in our design. It doesn't matter if the wall will be overtopped exactly once or that is not very much valuable to us. What we need is the wall will be overtopped at least once in next 3 years or next 50 years. That is what we are interested in. Okay, so these other probabilities are just for you to um, see what are the different kind of probabilities, but in terms of risk, this is what we calculate: 1 minus probability of not exceeding. Okay, that is the risk. This table here shows the system risk for different magnitude events over various observation periods. So observation period means the lifespan of your structure. So you design your structure, is useful life is 50 years or 500 years. So that is the observation period, and the actual event return period. So what value you use for that design. So you design 100 years return period flood. When you design your bridge, okay, you design for the flood to be 100 years. So up to 100-year flood event, uh, your bridge will not have any effect. But if it is more than 100, then the bridge will be flooded. That's the meaning of the return period used in design, whereas observation period means the lifespan of the structure. So your structure may be the bridge maybe you design for 25 years, or you may design the bridge for 50 years, even though you use the flood of different return period. So that's the risk that we calculated, and these values shows the risk for different return period and different observation period. So for example, if you design, so here return period is 100 years. Okay, so you design a structure with 100 years return period, but the structural design is for 100 years. So lifespan of the structure is 50 years, and then you see, and from the same line, and 0.39 is the risk. Okay, so if you design a structure with 100 years return period flood, and within 50 years, what is the probability of uh, flooding at least once is 0.39. The same way, the other way around, if you design a structure for 100 years lifespan, and then you use 50 years of return period flood, then the probability that the structure will be flooded at least once in its lifespan, which is 100 years, is 87%. All right. So this is frequency descriptors used by Australian rainfall and runoff. So different frequency descriptors, very frequent, frequent, infrequent, rare, and different frequency descriptors are there, right? And if you look at these values here, they all mean the same thing. Okay, the EY means accidents per year. So 4 EY means 4 accidents in a year, right? So if you are going to design water sensitive urban asset, then you use the stream flow value of 4 accidents per year. So stream flow, the stream flow can exceed that value 4 times a year, right? So you design your structure that way that it will be flooded 4 times a year. But you can say same thing by you are designing your urban sensitive asset at the 98.17% annual accidents probability, or 1 in 1.02 years, or 0.25 ARI. So they mean the same thing, but if you use this EY for the very frequent events, it is more easy to understand. For accidents per year is more easy to understand than saying 1 in 1.02 years, or 98.1% annual accidents probability. Similarly, if you are going to design a stormwater pit and pipe, you probably will use 10% AEP, right? So if you are using the 10% AEP, it is the same as 0.11 accidents per year, but it is difficult to grasp, difficult to understand what does that actually mean. So 0.11 accidents per year, but it is much more easy to say 10% annual accidents probability. Similarly, if you design a culvert, you will say 1% AP, then this in accidents per year. Okay. The AAP you can also say in 1 in certain years, so 1 in 50 years, 1 in 100 years, but when you use this 1 in this many years, then there is a chance of confusion of the meaning of that, especially the interpretation, how that is interpreted. So 1 in 50 years, especially by public, can be interpreted as the event will happen only 1 in 50 years, so which is not the case, right? So 1 in 50 means it has 2% annual accidents probability, so the flood can happen next year and it has the probability of 2%, right? So to avoid the confusion, this is not the preferred, but mathematically it is the same. And you can also calculate average recurrence interval. Okay, so ARI is another term.